Hey guys, welcome to my first math lesson video, so my second official lesson, and today we'll be talking about some things that you might not already exist and a little bit things that I kind of created. So we'll be talking about the Fibonacci family tree, about all the different sets of functions and numbers similar to the Fibonacci sequence, as you might know, which is, how you actually, you know what? I'll write it. So f of n plus f of n minus 1 is equal to f of n plus 1. And basically it's the same. You have some value which you start at, which you start at 1, and you add the previous, and we assume that's the previous is 0. So it would be 1 plus 0, which equals 1. And now the previous, because when we iterate it again, the previous will be 1. So it will be 1 plus 1, which equals 2. And then keep going, and going, and going. And so technically the first Fibonacci, because as we start at 1, that means it also goes from 1. So it goes 1, 1, 2, 3, 5, 8, and it does continue. But there is, you might think, well, you said family tree, that means there might be multiple. Yeah, just drop my pen, hold on. Yeah, there are multiple types of the Fibonacci sequence. There's the Fibonacci, the Tribonacci, but they're the only two that are really that well known, and even then Fibonacci is really the only one. And you get a constant from it called phi, which is an equation that you can write where it's f of n plus 1 over f of n. So the next Fibonacci number over the one that you have now, so let's say you have 5 over 3, which equals like that. But it converges to a value as n. You'd write it lim n equals 1 become 5. There's a few ways around it, but it's about this. And the value is 1.618 and so on, because it's like pi, an Euler's number. It is irrational and continues on forever. But before we get into that, before we get into the new things I add, I'm going to have like a kind of introduction-ish of how additions, well, not just how you can understand how different numbers relate. So we'll have a simple sequence: 1, 2, 3, 4, 5, and continue. The difference between each of them is just 1. So you just write it as n. For every n you choose, so 1, 2 of any number, it will just go up by 1. The sequence is just n. That's it. Which is a boring sequence, but it's really just how we count. And then you get a little bit complicated. So we go 1, 3, 5, 7, 9, and continue. The difference between these is a little bit more different. It's 2. I think, oh, the difference is 2. Maybe it's the 2 times table. But no, because if it was that, then you'd write it as 2n. So every number you input should give this, but 2 times, let's say, 2 is equal to 4. So what's the difference from this? 1, which means it's 2n minus 1. So what you do is you find the difference between, sometimes you'll not even be given this amount, you might be only given like 3 numbers. So you find the difference from the last number to the number previous, or just between 2 numbers like this. And then that difference is the coefficient, which the coefficient is the number in front of the n. And then you find the difference between the actual, what that actual times table would be, and this sequence. So because the actual one is 4, 6, and you can connect them, you see the difference is 1, so 2n minus 1. And like the previous video, I may give a few questions, but this is not really going to be much of, it's going to be a different type of teaching, since a lot of the stuff isn't exactly, I mean, I could kind of write like for the sort of questions that are like the stuff that I create, since there isn't really much on it. Anyway, getting off. So there's also other sequences like 4, 9, 16, and 25, and so on. The sequence you might know is n squared. So for any n, you times it by itself to get this sequence of numbers. You could also, the nth term, which is the when I write m and so on, you could also say as some function, which is kind of what the Fibonacci sequence is. We have kind of this function where f of x, which is how you write a function, is equal to x squared, which is kind of like a complicated way of saying x of m squared. That's how you write it more formally, but also a little bit more complicated. So when learning, you just, since if you don't really know much about it, you just want to write things like this, because this gets a little bit more complicated. But we will be going into a bit more complicated things. I will be doing videos in the future going slightly more simpler, but still interesting, like of kind of to do with sets of numbers. Instead of just the Fibonacci numbers, it's to do with factorials and how you can use factorials to produce prime numbers, or using the product function, or actually, because the product function is where you have, if you know what a product is, it's where you have the time multiplication between a certain number. So write it as this, k is like the last number, n equals 1, and n, so it'll be 1 times 2 times 3. Anyway, this is something we'll cover in a later video. Back onto sequences of numbers, which are more normally just addition sequences, but you can do multiplication. You can also have 2 to the n, which is an interesting one. So it's powers of 2. A power, this is a power. Can you actually see that? Oh, that doesn't even look like 2 to the n. There we go. So you would have 2, and you would have 4. Well, actually, there's just one more, which is 1. I'll explain that just a sec. 2, 4, and so on. So that's 2 to the 1, 2 to the 2, 2 to the 3, and so on. And it gets exponentially bigger, it's called exponential. But also 2 to the 0. And any value which is 2 to the 0, you have to write as a fraction 2 over 2, which equals 1. Any n over n is equal to 1. Even 0. 0 over 0. A lot of mathematicians and science people say that 0 over 0 is 1. There is proof to back it up, and I actually will go over that in the video. Okay, so with that as well, you can have, if you have n to the negative 1, you have n squared, no, you have n over n squared, which means if you have n to n, you know some basic math, you have multiplications that are similar, values that are similar, you cross them out, which means it would be 1 over n. So let's say 1 so negative 1 is just 1, so it's just 1. But if you have, let's say 2 negative 1 is equal to 1 over 2. So let's say we have, I'm going to have a collection of values, and you have to find the difference between them. So yeah, I could just do it, because a lot of sequences you normally need at least 3, but in this I'm going to make it simple. Since you have 3, it's 3n, but since it starts as a negative, which means the initial value when you start at 1 will be bigger than 3, which means it'll be equal to 4 minus 3n, and you could try with this, 3 times 2, which equals 6, 4 times 6. Oh no, sorry, I've done it wrong. No. You would have it the 3n behind, so 3n is smaller, so you would have it in front of the 4, because sum a minus sum b, if a is smaller than b, will be negative. So got that wrong. Minus, which starts as a negative, so if you have plane. This is the plane of positive numbers, and then it goes to negative. It would start, let's say, here, and then it would continue. We could kind of do this on a graph. If you know what Desmos is, on a graph we put 3x minus 4, and it will kind of match this. It will be minus 4. It will start at minus 4. But that's a different topic. Now, onto the Fibonacci sequence. We have f of n plus f of n minus 1 is equal to f of n plus 1. So the next number in the sequence is the sum of the first number, which will always be 1, unless something is applied to it, plus the previous, which is we assume to be 0. So 1 is the starting one right up here. This f of n is basically a function. But like it's set kind of. Anyway, so 1 plus 0, as we did earlier, which is 1 plus 1 equals 2, 1 equals 3, 3, that's not 3. I always do 3 as 1. 3 equals 2 equals 5. Write a 0 here, but I cannot do 5, 8, 19, and you just keep going. And then there's the other Fibonacci's, which you can just write as, you could write as T of n for Fibonacci, which is where you add the previous and also the one before that. We could write it as a T of n, or sometimes there is a weird way you could do f of n and then some subscript. This is a subscript where we have a little small number in the corner. So if you've ever wondered what that is, it's called a subscript, and a superscript is a number at the top. So anyway, back to the Fibonacci sequence. This we'll just write it as f of n plus f of n minus 1 plus f of n minus 2 is equal to f of n plus 1. So remember, the original value always starts 1 plus 0 plus 0. Now we do not assume this is minus 2, right? Oh, if you go even further back than 0, you can maybe it's a negative number. But we don't assume that, we just assume it's still a 0. Okay, so which is equal to 1. So the first number will always be 1 in the Fibonacci sequence. It's the Fibonacci family sequence of this. Now that means 1 plus 1 plus 0, which equals to 2. But now this is 1, 2 plus 1 plus 1. Our first different value, which is 4. And 4 plus 2 plus 1, which equals to 7. So it's 1, 1, 2, 4, 7. This also has its own constant, which is, you could write it, remember it, we do T of n. T of n plus 1 over T of n, which equals to, it equals to, I think it's some 1.8 with some numbers. Yes, 1.839, there we go, I remember. And it continues. And if you 8, 9 plus minus I know it's just sometimes you might find a secret pattern, I don't know. But there's a way that I kind of write the whole thing of finding a basically the Fibonacci family constant function. So you write it as f of n bracket delta k, and then you would have some capital N, which equals some constant. Now there is like a kind of interval, that's the right word, where it's greater than or equal to 5 for any n in the natural numbers, that would make sense. But I think this will be something that the title, the thumbnail looks like, will be less than or equal to 2. Yes, there is eventually, as this number tends to infinity, so you'd write it as f of n bracket infinity to k is equal to 2. So this could be called 2, could be called the perfect Fibonacci constant, or the perfect Fibonacci family constant, which as it tends, it gets closer and closer. There's the Fibonacci, the Tribonacci, the Quadrinacci, the Quintrinacci, and is the prefix or is this prefix of Nacci will just describe what number it was in the sequence. And as it continues, you can even try it yourself if you have, as I said, you have Desmos or a calculator. You write the sequence out, you find the biggest number, and then you compare it to 5, which is in a way you can call it 5 golden ratio. You can call it the Tribonacci constant. Then you keep seeing the difference gets closer and closer to like 1.9 recurring. And for any 9 recurring is equal to 1. So this becomes 2. So and now I'm just going to do a little bit of dissecting, because what is the delta k? What does all of it mean? So remember, f of n is 1 over f of n equals 10 to infinity equals the Fibonacci constant, or the normal Fibonacci constant. So we've got a ratio which is 1.618. And I wanted to create but this only gives the Fibonacci number, so you have to keep writing. I wanted to write an equation which is this one, describes so delta k, this means the difference between this, basically delta k is this. Delta k we assume goes to infinity. So delta is describing the difference between the one that you brains can't find. So one number in the sequence and the next, and the difference between that. And k is to infinity, so goes to infinity as you find the last two. Well, there is no last because it goes forever. We've just assumed it does we have the biggest Fibonacci with the second biggest, and we find the difference. That's what's basically this describing. N is which sequence, because there's the Fibonacci, remember, the Tribonacci, the Quadrinacci, the Quintrinacci. So this would be 1. This is 1, 2, 3, 4. I know this is kind of weird because quad means 4, but because of how it works, it's just shifted along one. So if you put 1 in here, it gives you the Fibonacci number, the normal constant, which is 5 in the golden ratio. So it gives you 1.839, and for 3 it gives you the constant, and it continues and continues and continues. This is a little bit complicated, so if you don't exactly understand too well, that's completely fine. But it's just very interesting. Also, there is another set of numbers which is kind of in the Fibonacci family, but it is not exactly included in that equation because it's weird how it works. Hold on. I have it in my bit of searching, but I had to dig around because it was in the book that I had finished previously. So because for some reason I thought I did it in my most recent one because hold on. Oh, I just lost it. Damn it. So this page is the book I'm working on right now of my stuff, which is called the real after numbers, or R subscript A. So okay. Real after numbers. And RA1 is equal to 2. RA2 is equal to 3. And RA3 is equal to 7. Now, the thing is with this sequence is, I don't even know what I've just taught you is about how to find the difference between sequences. It's like a really weird, it converges. I do know that as n tends to infinity, it does. So we do R of 1, R of A, n, which equals some R of A constant, R of A C, some R of A constant. It goes. Sorry, I had to just go downstairs for a sec. Anyway, we're talking about the certain variables I created, which, as I said, they're kind of weird. They're called the real after numbers. I don't know if I mentioned that. Yes, I just need to find them again. Okay, real after numbers. Okay. Where's my... I've left it on the floor without the cap on. That's just great. Okay, it's fine. So, the real after numbers are a set of numbers that I came up with in the shower. It was weird. Anyway, so you write it like this. So it's 2, 3, 5. No, not 5. 2, 3, 7, 12, 18, and 26, and so on. So it's basically, you pick some starting number. So if we have to pick the smallest starting number greater than 0, that is a whole number. So that's the easy stuff. With 1. And then to get to the next number, you have to choose the smallest difference, which is also has the same thing applied to it. Which means you can't start by 1. Oh, because another thing is, so the first number for first n, choose lowest whole before 0, which applies for both the starting number and the difference to get to the next one. But there's a key thing that must also be applied, the third rule, which is no number must be repeated. So see, the difference is 1, 4, 5. You could then say 1, 2, 3, 4, 5, 6, 7, and 8 will come 8, and so on. And no number must be repeated. It's like the I can't pronounce, but you might know the sequence where it kind of like goes all loopy and all cool. It's like a weird iteration of that, in a way, but it's pretty cool. So I created it, so it's kind of biased to say that, but tell me what you think. So you write the constants for it. So put that down. I'll go for the recent one. Okay, so R of A n plus 1 over R of n, which is very similar to the f, which is actually identical to f of n plus 1 over f of n, which equals some constant. And as it continues, it will, as n lim to infinity from 1, it will become 1, which is from the differences, which which is weird, but it seems to show. It just feels very odd how it becomes 1, which means it doesn't change, even if it does change. So eventually it stops, but it makes sense because it's meant to have every number. For every difference, it can't be repeated within the differences or the actual numbers that you get from the differences. And if you have, let's say, some number which is infinity, and you find the difference of infinity to get to the next one, it just stops because you can't have that, because that means they would be equal, which means the infinity would be equal, that means it would be the same. So it's a kind of a paradox, because if you have some infinite number n becomes the last number isn't infinity technically, because infinity is not exactly a number, so we just kind of say it is. So that means we have infinity, and we just change it by infinity. Infinity's already been used, which means we have infinity plus 1, which isn't a valid sum. So that's why it maybe equals 1, because it kind of just breaks. So it's very weird like that. It's quite interesting. So you'd have, we'd write this sequence, write the constants like this, where it's just fractions. So that's my brother. and then it, which is weird. So it does have a little bit of oscillation at the start, but then the oscillation stops as you get to like some really big real after numbers. Let's say okay, like this one. So we have 5, 6, 4 over 5, 8 equal to 1.681. It's very close to 1, and I'm pretty sure it goes to 1, because as I said, you can't get more than infinity. I mean, you can. There's this collection of numbers which are to do with massive numbers like omega, subscript plus 1, plus 2, and stuff, which basically is to describe numbers that are really big. And if you've ever heard of alpha null, which is the cardinality of the set of all numbers. So the cardinality of technically infinity is equal to alpha null. I can't draw alpha null, but if you look on the internet or like Wikipedia, you'll get a picture of alpha null. So today I don't really think I have any questions to you, but that's fine. It was mainly just meant to be a teaching lesson, since I'm going to do another one, since I've been busy, since I've been on holiday for about a week, so I haven't been able to do any videos. But this basically concludes my simple video on the kind of family of Fibonacci numbers. So yeah, if you like it, then check out my other video. Actually, no, I don't have one other actual video. So yeah,